Okay, folks, today we're starting a new chapter, and this is going to take us a little bit away from the structure of the atom for a little bit, and then we're going to finish off the chapter by talking about where the electrons go exactly in the atom, because it's a little bit more complicated than just saying that they go on the outside, but we'll get there. So first, to understand this chapter, we have to understand what electromagnetic radiation is. Electromagnetic radiation is a kind of radiation combining magnetic and electric fields. This radiation makes up so many things that we use in our everyday lives, like cell phone signals, Wi-Fi signals, visible light. So the light that we see that comes in our eyes, that is electromagnetic radiation, and radio waves. Okay, and there's a lot more that goes into it. If you want a visual of what electromagnetic radiation looks like, it looks like this, okay, where you have this oscillating, so you notice here that there's two waves. There's one that goes up and down and one that goes side to side, and it's that combination of the two that makes it electromagnetic radiation. Okay, so again, like I said, electromagnetic radiation, it's all of these things and more. Okay, so the visible light that we see in our eyeballs, the Wi-Fi signals that get sent, cell phone signals that get sent, radio wave signals, all of those are made of the same thing, and it's electromagnetic radiation. Electromagnetic radiation travels in waves. When we talk about waves, we need to learn some terminology. There's 3 different ways that we can describe a wave. The first is the wavelength. The wavelength is the distance between 2 peaks. Okay, this is your wavelength. And it's measured in meters because it's a length, right? So the length between 2 peaks. Next is amplitude. Amplitude is the height of the wave measured from the middle, okay? So here's the middle of the wave, and it's the height up to the top of the peaks, okay? So this is amplitude. And it is also a distance, as measured in meters. And again, it's the height of a wave. And then frequency. Frequency is the number of waves that pass a certain point per second. Okay, and I'll give you some examples of frequency in a second here, but the units on frequency are because it's number of waves per second, the second is on the bottom of the measurement, so it's like the number would go here and then per second. Okay, so that's what it looks like. So you'll see per second. Another unit that is used for frequency is hertz, which is abbreviated Z, okay? And then lastly, you guys might see S to the -1. S to the -1 literally is the per second thing. So if you guys ever see anything raised to the -1 power, it means it's underneath the fraction. So like 3 to the -1 power means 1/3. And like 2 to the -1 power would be 1/2, and so on. So like S to the -1 is like the number over seconds. Okay, so anyway, if you just see that raised to the -1, that's what that means. So there you go, waves per second, that's what frequency is. And let's see, moving forward. Okay, so take a look here, okay? These waves have these properties here. So I want you guys to take a look based on the definitions that we just figured out. Which of these waves has high frequency, a long wavelength, a low frequency, and a short wavelength? Go ahead and pause, figure that out. Wave A or B, which one would fit in these blanks? Go ahead and pause and figure that out. Okay, hopefully you guys said the high frequency was wave A, the long wavelength was wave B, The low frequency was wave B, and the short wavelength was wave A. Okay, so notice again, so a high frequency means there's just a lot of waves in a given space. Okay, that's what a high frequency is. Here, there's very few waves in this given space, so there's going to be a lower frequency there. And I want you guys to notice the something. If there is a high frequency, the distance between the waves gets shorter because there's a lot more waves in a given space. So if as your frequency goes up, as your frequency goes up, your wavelength goes down. Okay, notice down here, our wavelength is really large and our frequency is low. Okay, so they have opposite relationships. So as one goes up, the other goes down. All right, so when we describe waves in electromagnetic frequencies or electromagnetic waves, there is a formula that relates frequency and wavelength. And the formula looks like this. C equals lambda nu. Okay, so let's label these guys. So C is the speed of light. And the speed of light is constant, that this number never changes. It's 3.00 times 10 to the 8th meters per second. And then this guy is the Greek letter lambda, and it represents wavelength. Again, measured in meters. And then there's this guy, which is the Greek letter nu, and it measures frequency. And again, you might see hertz or per second. So what this formula tells us is that if you multiply the wavelength times the frequency of any wave of electromagnetic radiation, you'll get the speed of light. Okay, this also tells us that electromagnetic radiation always travels at the speed of light. It only has one speed, and that's the speed of light. So if you multiply these two, you get the speed of light. Also, guys, I want to point out that you could also make this into one of our triangles that we're used to working with. So it would look like this if you wanted to use it as a triangle. Please do copy this down. This will be helpful for you on your homework. Okay, so if I ever ask you a question, hey, what's the wavelength? You would cover the symbol up for wavelength, and then you would do the speed of light divided by frequency. If I'm ever asking you what's the frequency, you would cover up the frequency, and then you would do the speed of light divided by wavelength. Okay, so this is a handy little triangle to have in mind. So let's take a look at how this formula is used. So let's say, okay, we've got a wave. What is the wavelength of a wave with a frequency of this value here? So again, if they're asking us to solve for wavelength, that's this symbol. Okay, so like I said before, if we're solving for it, you cover it up. And then what's left over is the math you need to do. So we need to do the speed of light divided by frequency in order to get this answer. So our wavelength is equal to the speed of light divided by frequency. The speed of light is 3.00 times 10 to the 8th meters per second. Divide by the frequency, 2.76 times 10 to the 14th. S minus 1. Folks, do you guys notice I'm using parentheses here? This is super important. Okay, so your calculator should have parenthesis buttons. Please use parentheses when you put this in your calculator. So like when you're typing this number in, hit parenthesis, and then 3.0 times 10 to the 8th, close the parenthesis, hit the divide button, and then parenthesis 2.76 times 10 to the 14th, and then close the parenthesis, and then hit enter. If you don't use parentheses, it will often give you the wrong answer because it changes the order of operations. So just keep that in mind. Okay, so we get 1.09 times 10 to the negative 6 meters is our wavelength. Okay, let's take a look at another example. If this one, we're looking for the frequency of a wave. So if you guys take a look, here is our little triangle. We're solving for frequency, which is this number here. Cover it up. So we're going to use speed of light divided by wavelength. Okay, so our frequency is equal to the speed of light divided by wavelength. Speed of light is this number here, divided by our wavelength, 5.6 times 10 to the negative 13 Okay, again, when you put this in your calculator, make sure that you're using parentheses. And when you crunch this out, you get 5.4 times 10 to the 20th s minus 1. If you haven't tried this in your calculator yet, please do so. Please try doing both of these and make sure that you can get the right answer. If you can't get the right answer, please raise your hand and make sure you get help. If you're doing this in class or if you're doing this at home, please make sure you come and get help figuring out how to do this in your calculator. Okay. All right. So the last topic we've got is, now that we've described waves, let's talk a little bit more about this electromagnetic spectrum. Okay. So if you guys flip to the next page, I've got this spectrum of electromagnetic. Okay. So notice this is symbolizing the different frequencies we can see in the electromagnetic spectrum. Down here is really high frequencies. Down here is really low frequencies. I want to keep in mind, though, guys, that all of these, okay, every little chunk of this wave travels at the same speed, which is the speed of light. Okay. So I want you guys to notice also in this little spectrum, there's a tiny little sliver right here. Okay. In this little section of the wavelengths, this little tiny section, if we zoomed in, we would see the visible spectrum of light. Okay, so in the entire spectrum of electromagnetic radiation, we can only see this tiny little sliver with our eyeballs. Okay, and it is on the Roy G. Biv spectrum. So if you don't have colored pencils or anything to fill this in, please label the colors Roy G. Biv. Oop, this needs to be moved down. Boop. Okay, so the reds are closer to the 700 nanometers and the violets are closer to the 400 nanometers. Okay. So this is, again, your visible light. This is the only part of the electromagnetic spectrum we can see with our eyes. And then there are other sections that we do interact with. So I want you guys to please add these lines here. We're going to add 3 over here and then 3 over here. So down on the low energy part of it, if you guys notice, when the wavelengths are longer, this is a lower energy wave. Over here, we have a higher energy wave. So higher frequency means that it's carrying with it more energy. Lower frequency means it has lower energy. So the lower energy wave are our radio wave signals. Okay. After that come microwaves. And yes, I'm talking about the food cooking microwaves. Okay. After that, we have infrared. And infrared is basically what we see as heat on those heat-seeking cameras. Let me see if I can pull up a picture, actually. Infrared. So if you look through an infrared camera, you guys can see where it picks up different heat signatures. So that's what I'm talking about for infrared. It's basically what heat looks like if you could see it with your visible eyes. Okay, so that's infrared. After that, we have the visible spectrum, and take a look what's next to infrared. We have red. Okay, so they are related, infrared and red. And then we get our visible spectrum, and then we're getting higher and higher in energy here. So here is violet, is the last visible color that we can see. And I think you guys know this. What's next in energy higher than a violet? Any guesses? It is an ultraviolet. Often referred to as UV radiation. This is higher in energy, and is actually so high in energy that it can give us sunburns. So this is why we wear sunscreen, to protect from ultraviolet radiation, because this spectrum of the electromagnetic, radiation is harmful to our cells. Okay, it can break down our cells. After this, we have X-rays, which we know for sure are dangerous. And then at the very end, we have gamma radiation. Gamma radiation is super high energy and is very, very dangerous to humans and all living things. It is put off by the sun. However, our atmosphere protects us from incoming gamma radiation, which we're very lucky for, because we would be bacon if it came through the atmosphere. Okay, so this is the whole spectrum. There are other things in it, like Wi-Fi signals are around here. Okay. They're between radio waves and microwaves. Yeah, so anyway, all of these things, everything that you guys see labeled on here is all made up of the same stuff, which is electromagnetic radiation. Okay, and we're going to continue to talk about it later, but that's the end of our notes for today.